Okay, so now we're going to get into, as promised, a discussion about elements. All right. So, what are elements? Elements are basically substances that cannot be broken down chemically into simpler substances. All right. So that's basically the definition of an element. It's a substance that cannot be broken down into simpler substances by chemical means. Now, there, well, basically elements are the fundamental building blocks of pretty much anything material. And as stated here, all known substances, let me go back to my full screen here, all known substances on Earth are formed as a result of a combination of more than 100 elements. Now, as far as how the elements are distributed in different locations, it depends on where we're talking about because there's no equal distribution of the elements in nature. But we can determine or can state that oxygen is the most abundant element in the human body, and it is also the most abundant element in the crust of the earth, 49.2%. And in the universe, however, the most abundant element is hydrogen, which is 91%, and then the second most abundant element in the universe is helium, which is 8.75%. All right, so what I just described, plus some other elements in terms of their distribution, is given in these pie charts here. So this is basically what I just talked about in terms of the universe. Hydrogen is the most abundant element. Then the next would be helium. And then all other elements would be about 0.25% of the elemental composition of the universe. On Earth, what you'll find is that the most abundant element is oxygen. Then the next in line would be silicon. Then you have aluminum. And then as you can see, we have some others here whose individual abundance is no more than 4.7%, which is iron here. And then they become less and less as we look at the other elements. And then as far as the human body is concerned, as we said before, oxygen is the most abundant element, followed by carbon, followed by hydrogen. So these elements here account for, I would say, about 90% of all the elements in the human body, and then the rest, like nitrogen and calcium and phosphorus, would be the rest, right? Nitrogen is about 3%, and calcium and phosphorus and all the others would be less than that. All right. So that just gives you an overall picture of how the elements are distributed in the human body, on the Earth's crust, and in the universe. All right. Now let's talk about the names of elements. And there's some history behind the names of certain elements. In some instances, the name is based on different languages other than English, that is, right? So for example, iodine, its name came from the Greek ios, which means violet, and that's because that's a color of iodine if you were to see it. The name can also be based on some property. In this case, the language is Latin, and the example that is given here is fluorine. Now, fluorine is a gas, but the actual name comes from a compound which contains fluorine, which is known as fluorspar, which is a solid, but it has a very low melting point. So because its melting point is low, then, if the temperature is relatively low, not too low, but relatively low, what you'll find is that it will become liquefied and start to flow. So therefore, the Latin word here, I don't know if I'm pronouncing it right, fluor, basically means to flow, and that's where fluorine comes from. All right, so that just gives you some idea as to how these names are derived. Here's another example. Now, this is a German example, bismuth. Now, I don't know the connection between bismuth and Weissmass, but German Weissmass mean white mass, and therefore, basically, that's the name of this particular element. And then in this case here, and this is not the only case, but in this specific case, the name of this element is based on a country, actually. This element is known as germanium, and it is named after Germany after being discovered by a German chemist. And then a last one here is where this is one that's named after a famous scientist, Einstein, Einsteinium. So this is named after Albert Einstein. So as you can see, the sources of the element's name can be wide and varied based on color, Well, firstly, based on different languages, and you know, they can be used to the terms in the different languages can be used to describe different properties associated with the elements, as well as based on the name of locations and important famous scientists. Now, in chemistry, we tend to use shorthand symbols for representing elements. All right, and the symbol itself can represent the element itself, but it can also represent one atom of the element if we're writing down the formula which contains that element, and of a compound that contains that element. That's what I meant to say. And then here we can also use the symbol to represent a particular quantity of the element. Now, there are some rules governing the symbols of the elements. You don't need to know these rules. It's simple actually. Basically, the symbol can have either one or two letters. If it has one letter, then that letter is capitalized. If it has two letters, then one letter is capitalized and the other one is lowercase. So, in terms of one letter examples, hydrogen has a symbol H, carbon has a symbol C, and then in the case of two letter examples where the first letter is capitalized and the second one is lowercase, here's one example: neon, the symbol is Ne, and barium, where the symbol is Ba. All right, so these are just examples of the symbols for different elements, as you can see here on this slide, right? So some of them are one letter examples, and in some cases what you'll find is that most of them will have the same letter, especially the initial part, as the name of the element. So Al for aluminum and I for iodine. All right, but there are other instances where there seems to be no connection between the symbol and the name of the element itself, such as Hg for mercury and Ag for silver. And the reason for that is because the initial names of such elements were different from the names that we now know in English. So, for example, the present name of this element is antimony, right? The symbol is Sb, and that's because its previous name was stibium. Or in the case of copper, where the symbol is now Cu, and the reason why that's the case is because the initial former name is cuprum, and we can see some other examples in this list right here. So that's why you can see something like the symbol for iron is actually Fe, and that's because the initial former name of iron was ferrum. All right, so that's basically why we observe that disparity between, in some cases, between some symbols and their current name in English. Okay, now you may or may not recognize this, but this is what we call a periodic table, and it's a special collection of the names or symbols of different elements, and they're placed in a particular order. And there's a reasoning behind that, and we may get into the reason why they have this special arrangement, right? But for now, all you need to do is accept this as it is, that there's a reason why we have this special arrangement, all right? And we're going to get into some definitions later on when it comes to like atomic numbers, which are these numbers that you see here within the box for each symbol for each element, all right? But I want to talk about some broad categories of elements based on this arrangement here, this table right here. Now, what you'll find is that most of the elements that are to the left of the periodic table, they are basically known as metals, all right? And we may get into what we mean by metals, all right? But I'm quite sure you're familiar with metals, again, from your everyday experience. You know, we're talking about things like copper, iron, zinc, and so on. Those are metals, right? So they tend to be to the left of the periodic table. And then to the right of the periodic table, you have what are known as the nonmetals, which, as the name suggests, are not metals. Now, there is a third grouping, a minority grouping of elements, which are known as metalloids. Now, the metals in this periodic table are are in the blue shaded box. The nonmetals are in the green shaded box, and the metalloids are in the gray shaded box here. So we're talking about boron here, silicon here, germanium, arsenic, antimony, tellurium, and polonium, right? These are called metalloids. And the main reason why they are called metalloids is because they have some characteristics in common with metals and other characteristics in common with nonmetals. That's pretty much the reason why. So they're not completely over here on the metal side, and at the same time, they're not completely over here on the non-metallic side. And you'll notice also in this periodic table, there's this thick stepwise line, this black line here. That black line basically represents, that black line there basically represents the line of demarcation between metals and non-metals. So the metals would be to the left, the non-metals would be to the right, and the metalloids would be on one side or the other of the line, the boundary between the metals and the non-metals in the periodic table. Okay, we're going to stop here. The next topic we're going to talk about is another term that is important in chemistry, and that is the atom. All right? Until next time.